Then, well, the cosine x have derivative of negative sine x. The derivative of sine x is cosine x. Alright, that's two conclusions we had from this one. And then the third limit we had seen before, for the limit of x approaches to 0, 1 plus x to the 1 over x equals e. Right, so if we take both sides to the power of x, of course that's thing containing the limit, so on the right side it also contains the limit, right? So the limit will be the limit of x approaches to 0 of e to the x here. Right, the limit of e is same thing as e, then we approach the power x to it. That's the limit as x approaches to 0 of e to the x is same as 1 plus x. Use that definition, or use that transformation or property. We have derivative of e to the x respect to x, that is e to the x. So this one is a little easy to illustrate. That we have is the limit definition that h goes to 0, e to the x plus h. I don't have to write the difference of quotient formula, I believe. Minus e to the x over h. Which when we see as x approaches to 0 for e to the x is equivalent to as x approaches to 0 of 1 over 1 plus x. Right, so that the lucid here, right, e to the x plus h could be e to the x times e to the h. We have a factor of e to the x could be factored out, and we have e to the h minus 1 over h. We factor out or take out the e to the x since that's not related to the h variable, and e to the h as h approaches to 0, that's 1 plus h. Hence, I think I don't have to show step by step very detailed, right? We have 1 plus h minus 1, which is h over h. Which will remain our derivative to be e to the x. Right, so that is what we have. Right, so 3 formulas overall. We had seen 3 additional formulas. Besides something to be very apparently clear, we have that derivative of constant equals 0, derivative of x to the n equals n times x to the n minus 1. And for some trigonometric function, sine x has derivative of cosine x, cosine x has derivative of sine x, negative sine x. But be careful with the negative sign. And I can tell you the property that, well, derivative for sine, secant, and tangent, we have result to be positive. Derivative for cosine, cosecant, and cotangent, we have co in front, we'll have the result to have negative sign. Now we'll see what they are, but to remember that. Now when we're starting with trig function, that is a positive result. When we start with co of trig function, like cosine, cosecant, cotangent, those things will have negative results of the angle of the trig function. But like here, sine will have derivative to be cosine, cosine will have derivative to be negative sine of the inside angle. And then e to the power x has derivative to be e to the power x. Sometimes e to the power x, if you sometimes, right, like the power of e is kind of trickier to write. It's written as exp of the power. And maybe like something power like very hard, negative like x minus the mean squared over 2 sigma squared. And maybe something like that. It could be written as exp of negative x minus mu squared over 2 sigma squared. And sometimes it could be written as this equation or this expression that we have e written as exp of the expression will be a little bit easier to read, right? Because when for printing on the paper or for handwritten, it is hard to distinguish if this larger piece, relatively larger piece, is a power or maybe just e minus something. It will be hard to see, right? And but if we have written in that way, that will be more acceptable, and still it is understandable by other people, right? That is one way to write the e as an exponential function, as a base. Right, so that's for information. And well, so far that's the formula we have. I ask you to prove this one, I ask you can try to prove the cosine, you can try them. I had sine and e done for you, right? The constant also done for you already. So that are the formulas we have. We'll see something more in the later chapter, right? We have 6 trig functions, we only see 2. We have exponential function, we didn't see log yet. And for something else, right? We have trig functions, we'll have inverse trig functions for something like arc sine, arc cosine, arc secant, arc cosecant, arc tangent, arc cotangent. And you will see also, right, the derivative. Now we see the function one by one. For f of x equals x squared minus 2e to the x, or the original we say the combinations, the linear combination is still working, like coefficient is still coefficient, sums difference is still sum of difference of derivative. X squared will be 2 times x to the 2 minus 1. And this 2 is coefficient. We have e to the x as the function here, then derivative of that is still e to the x. Right, then we have 2x minus 2e to the x to be its derivative. It's not necessary in that case to factor out the 2. If you want to, it's fine, but leaving that expression is more favored, right? To leave that, since they are not same type, right? Usually, even though we have same coefficient, but we don't have to factor it out. Actually, leave like that will be a little bit good. Maybe not that much benefit, but it's a little bit more clean than we factor it out, kind of. Right, so try the next one. F of x equals cosine x over 2, 5 of x squared minus e to the x. This function, well, this cosine x over 2 has no problem. We say, well, over a constant, we could just leave it. But this variable is on the bottom, will cause a little trouble that we need to flip it up. Right, so clean it, or transfer it to a doable way, to a doable expression, 5 times x to the negative 2. Only the middle term need to be transformed. The first and third is okay. That we can get the derivative of cosine is negative sine x. Negative sine x still over 2, the middle plus 5 times negative 2x to negative 2 minus 1. Right, that's the product rule applied. I mean, the power rule applied. Sorry. We have to exist something, as I mentioned in accident. That well, we do have product rule that occurs when a function is a composite function of a product of two expressions. It is somehow the way composite, but it still is the combination. I'll have linear combination like the scalar multiply, or adding and subtracting, we have a product or quotient of two functions also is applied. We'll see that actually in the next section. But anyway, here is the power rule. I'll take the power down and power minus 1. E to the x, derivative is still e to the x. Right, then we simplify a little bit to a nice understandable way. That is negative 10 x to the negative 3. Only again the middle term is a main concern. That's the third power will be stay on the denominator. Right? Negative third is going to flip down. And negative sine x over 2 minus 10 over x to the third minus e to the x will be our derivative of this function. And similarly, we get a function y equals 2 sine x minus 3 over x plus 7 e to the x. We again need to simplify or transfer the second term, since that is a rational expression, have x on the bottom, so we need to flip it to x to the negative 1, right? Flip it up to x to the certain power. Which means at least make it able to apply the power rule. Right? So then, like that, we need a step to transform. Then we find the derivative. Right? Sometimes we cannot directly find the derivative from the function. We need a little bit some other thing to do, like here. Like that, we get the derivative of sine is cosine of x. The coefficient still stays. Negative 3 times power is negative 1. Right, power is negative 1, so carry that down. And the power of x will become negative 1 minus 1. And the derivative of e to the x is just e to the x. It is not copied down simply, but just taking the derivative of e to the x is same as e to the x. Later we'll see some tiny thing that may change. That we can simplify it to cosine of x plus 3x to the negative 2. Or the product that will be simplified, and then the power of x is negative 2, that will flip down to 3 over x squared. Right, that so far is the formula we have, and the application you could try to see. Oh, well, the next topic is rate of change. Right, so in physics we have position function, we have the t and s. Right, so for t1 and t2, that we get s1 and s2. That is a position function curve. Could be something, time, right? Then we have S1, S2, T1, T2, that we have, first of all, our average velocity. This, by definition, is the velocity on the average path, right? So along the path, we have S1 and S2. That is the distance or displacement, right? They make going, like going this way, move right? And for the time along the path, it's moving. So the distance over the time is called average velocity. And that thing is called average velocity. So some example maybe you have seen in physics already. Right, I will use that space that picture later, but so we have a short example. Right, an object height s and time t. S here, and the time t is a position function that st equal negative 16t squares plus 100. All of them are lowercase. I find average velocity. Over 1 second, 1 to 2 seconds, over 1 to 1.1 seconds. My two things asked. So average velocity is difference of the position over the difference of time. Right, three things we need to find. S of 1. Negative 16t squared plus 100, that is 84. Right, 1 squared is 1 times negative 16, that's 84, then plus 100 is 84. At 1.1. Right, that's negative 16 times 1.1 squared. That's 19.36, and that's 80.64. And the third one, negative 16 times 2 squared plus 100 is 32. So first one over 1 to 2, that is S2 minus S1 over 2 minus 1. That's difference of the position over difference of time. Right, that's 32 minus 84 over 2 minus 1, which is negative 52. I didn't mention about the units. Here, the height s is in feet, the time is in second. So we have average velocity of negative 52 feet per second. I forgot to mention. Right, the height is the unit of feet, the time is the unit of seconds. Right, that's over the 1 second to 2 seconds, we have a average velocity of negative 52 feet per second. Right, then over 1 second to 1.1 second, that's 80.64 minus 84 divided by 1.1 minus 1. Well, you can use calculator to find it. 80.64 minus 84 divided by 1.1 minus 1. That's negative 33.6. Feet per second. Right, so that is how we find the thing called average velocity. Average velocity is the distance it moves over the time it takes to move. Right? So even though it's a curve, but if we take it averagely in that velocity, then it will move the same distance by the time passing, which means from 1 second to 2 seconds, it goes from the position at 54 feet to the position at 32 feet. If we moved 1 second with that average velocity of going down 52 feet per second, it will also move 52 feet downwards. Similarly, from 1 second to 1.1 second, the average velocity is negative 33.6 feet per second, which means if we moved down with this velocity, for 1 second it will move down 33.6 feet. So here we have 0.1 second it take, so it moved down is 3.36 feet. From 84 feet above to 80.64 feet above, that is 3.36 feet moving downwards. Right? So that is what average velocity means. For the same of time, that is the velocity, and by that velocity it will move the same distance as we have. This question here, if you have a little bit idea of physics, right, is free fall. An object is free falling from a height of 100 feet and dropped to some surface or to something from 100 feet above the ground level. Right. That is what it is. And that we have is called average velocity, which if you still remember, right, that is something similar as difference of quotient. Right? And from the difference of quotient, if our change of time we had seen before was as the time changing, right, from a longer interval to a shorter interval, then if our change of time is extremely short, that we will get is called the instantaneous velocity. Right, before is the average velocity, is the velocity of a certain interval. Right, but once we get the h2 as approaches to x1 very closely, we'll get a instantaneous velocity. The slope at t1 is the rate of change, the rate of change of distance at time 1. And the rate of change of distance, in other words, is called the velocity. Right, so once we change the delta t goes to 0, which the change of t which will affect to the change of position function. In the view of calculus, we say, well, the difference between t2, t plus h of the position over the difference of time, we call that h, is called the velocity function. The velocity at the time t, which will be the rate of change at the time t, which is when the average velocity when the time changing is approaches to 0, that we get the position changing over the change of time, that the change is of time is small. That is what we have is called by definition is the derivative of the position function. Right, so how we find the instantaneous velocity or velocity at a special time for all the time being collected together is a derivative of the position. Right, so velocity is change of position in the short-term conclusion, right? So the change of position in calculus view, at any time the velocity will be the derivative of the position function at any time. Appropriate domain of time. So we see a short example. Right, initially it's going up as a velocity of 16 feet per second. Due to the gravity, then the person will going down. Right, 32 feet above the water is the diving board exists. That is 32 feet above. That we have a position function to be negative 16t squared plus 16t plus 32. Three questions asked. Now, when does the diver hits the water? And what is the diver's velocity at impact? Right, that is the question. Right, so a diving board, the diver is jumping, and here is a pool that the diver first going up, then going down to the dive. For this distance from the board to the swimming pool, that is 32 feet. Which means the initial, when it hits the water, that's 0 feet. Right, so actually the first question is looking for the time that the diver actually from moving up then moving down to hit the, not hits the ground, but hits the water, to hit the water. So the first question actually is asking for the time that the position equal to 0. Right, so we have the position function that is negative 16t squared plus 16t plus 32 equal to 0. If we divide every term by negative 16, the equation stays. Of course, we divide that by the same thing, that equation stays. We'll get t squared minus t minus 2 and we can factor as t plus 1 times t minus 2 because 1 minus 2 is negative 1, negative 1 times negative 2 is negative 2, right? That's how we factor. Therefore, we get t plus 1 equals 0, or t minus 2 equals 0, t equals negative 1, or t equals 2. Right, as commonly accepted, the time is fluid positively, so if we set the initial time to be 0, it can only goes positive. That's what is widely accepted now, right? So for t to be negative value, it's ruled out. Only take the t to be 2. The second question, asking for the diver's velocity at impact, which we need to figure out the velocity function, and then at impact the time is 2 as we figured out already. So velocity function is negative 16 times, or we write it in more detail. The velocity function is the derivative of the position function, negative 16 times 2, t to minus 1, 16 times 1 plus 0. Right, that's what we had seen using the power rule, right, which is negative 32t plus 16. Right, I think that the velocity of 2 is just negative 32 t plus 16. That is negative 64 plus 16, which is negative what? 48. Feet per second. Right, so in this section, we have all the formulas had seen. We had seen that the average velocity is average rate of change, which is the difference of quotient of basically refers to difference of position over the difference of time. Right? And then when the difference of time yields to 0, the average velocity yields to instantaneous velocity. That we can find instantaneous velocity by finding the derivative of the position function and substitute whatever we need, whatever we find for time or whatever given for the time, right, into the position function. So that is the position and velocity. Right, later chapter we'll see the acceleration, right? Not only the velocity, but next is the acceleration, which, well, acceleration of free falling we can see is negative 32 feet per second due to the gravity of Earth, right? And on different planets that will be different. And acceleration due to force will have maybe different functions, right? And we'll see them next section, next time. And as I mentioned before about the product, about the quotient, that rule we will also see them, right? This time we'll only see the linear combination, which is scalar multiply and sum or difference with other formulas. If you still remember that x to the n, the power rule, the sine, cosine, and the e to the x. Right, those things are what we see. Try to get them. Right? Try to get them. But we'll see some other trickier formula next time.